Section 11.9, the Trapezium Rule. So not all functions can be nicely integrated, therefore it's not always easy to find the area under the curve. So mathematicians came up with some nice numerical methods of finding areas under a curve. So for example, here's our curve, y equals f of x. If you want to find the area under the curve between the lines x equals a and x equals little b, so if we want to find this area under the curve, you will be looking for the value of the integral. So you will integrate the function f of x between the limits a and b. Now, if you can come up with another way of evaluating this area, then depends how accurate you are, the value is going to be, should be pretty close to the integral. So the way you do it, we're going to learn, one of the ways of doing it is to use the trapezium rule. So the idea is to split the area between A and B into strips. There you go, so vertical strips of equal depths, if you like, the equal width. Now each of those strips is going to be, the top values of each strip are going to be joined, those 2 points, and you're going to have a series of trapezia. It's by freehand, there you go. There you go. Now, depending where the curve is, like for example this trapezium here, if you join the 2 points over here with a straight line, the curve is going to go above this, so the trapezium is going to be a slight underestimate. Now, if you have a concave curve, like over here, and you join the 2 points, then the curve is going to be below the top side of the trapezia. So the trapezium, that particular trapezium, would give an overestimate. So the depth of each trapezium is going to be we're going to denote it using letter H. So we split it into equal width, trapezium of equal width H. Now each of those widths is going to be, now in the formula booklet is given as b minus a, so puts b, take away a, divided by how many trapezia we have. I would really recommend you don't ever use this formula to find the value of h, so don't use it, because people always tend to make mistakes while trying to use it. So I would suggest you use common sense. They normally use the wrong value of n, and I will explain in a minute why this is so. So the formula is given in the formula booklet, so that integral can be approximated by, and then you go the half of h, so it's h over 2. Then you're going to have the first value of y, and the first value of y is simply the value of y you're obtaining by subbing the first value of x that you are evaluating it at, so it's called y0. Okay, then you get the last value of y, and the last value of y is going to be yn, so it's whichever one is last value that you've got. And then plus 2 lots of all the other y values. So this one here is going to be y1, then you've got y2, etc. up to yn minus 1. So it's y1 plus y2 plus all the others up to the one that comes just before the last one, so n minus 1. So where did it come from? It's just simply by adding individual areas of each trapezium. So the first trapezium, the formula for the area of a trapezium is the two parallel sides added together times that result by the height between them, and then divide everything by 2. So the first trapezium is going to be a half of h, because you'll be dividing by h, dividing by 2, and it's the first y value plus the second y value. The second trapezium, you're going to have the same, so that's y1 plus y2, and then you get the third one trapezium, that's going to be h over 2, third value of y, which is called y2, and all the way up to there. The last one, let's do like the last by but 1, so n, if that's going to be your n plus 1, this is going to be your n value, n trapezium, this is going to be n minus 1 trapezium. You will have h over 2, and then here you will have n minus 1 and n minus 2 plus y n minus 1, and the last one we will have h over 2 y n minus 1 plus y n. So if you add them all together, because you're adding the areas, all of them will factorize h over 2 out, and you'll have y0 plus y1 from the first trapezium, y1 plus y2 from the second trapezium, y2 plus y3 from the third one, and then you're going to have yn minus 2 plus yn minus 1, then yn minus 1 plus yn. There you go. So you have h over 2, and you have y0 will only appear once, and then you will have y1 from the first trapezium, but that's also the side that's shared with the second trapezium, so you have y2. Then you get y2, which is the side from the second trapezium, it's also shared with the third one. And then you've got y3 will have the one, and the next one will have y3, so that these will also have shared, so you will have these appearing twice as well. So all the ones apart from the first and the last y will appear, which appear only once. You can put them together, and then you've got 2 of all the others. And that's where the formula comes from. Formula is quoted in the formula booklet, so it's approximately equal to, it's very close in value though, and it's really brilliant for the functions that is not very easy to integrate. There you go. So my advice to you is, do not use the formula for finding h. Find h using common sense. So even doing things like drawing a number line, or most often just looking at the table of values and seeing what is the jump between the values of x, and that will give you that h value. So the jump between x's in the table of values is what your h is equal to. So we're going to have a go at some questions from the textbook. We'll go through one example, and there'll be a couple of different ways of doing it. I think the number of strips will change. Let's have a look. So it's example 24. Let's just very quickly mention it before we move on to example 24. The reason people make mistake with that n is because if you see you're using one, let's for example in this example we've got 1, 2, 3, 4, 5, 6, 7, 8 values of x that you will have to find the corresponding values of y for, but in terms of how many trapezia we've got is 1, 2, 3, 4, 5, 6, 7, because don't forget you will have the starting point and the end point, and in between this you will have one less gaps than the actual values involved. So therefore n is the number of trapezia, so not the number of x values involved in the question. So example 24, you've got the diagram showing function. So let's have a look at the actual function. It looks a bit like a parabola, but it doesn't. It's actually y equals sec x. And then we are asked to find the area. We're going to look at the finite region R between 0 and pi over 2. And the table of values is given as well. So we've got some values, and it's quite typical. You'll have most values given, and you'll probably have to find a missing value as well. Here we've got the most two values need to be found. We've got 3 values that are given. There you go. So in part A, we have to complete the table. So over here we are going to find what sec pi over 6 is. So this is the same as 1 over cos pi over 6. Put it into the calculator. That's going to be 1 over root 3 over 2, which is 2 over root 3. Using the calculator, you will have 1.155. And then we're going to look for sec pi over 4. Again, put it into the calculator. Cos pi over 4. That's going to be root 2, which is 1.414. So we've answered question part A of our example, which is complete the table of values. For part B, we have to use the trapezium rule with all the values of y in the completed table to obtain an estimate for the area. So quote the formula. So the integral, or the area, is going to be h over 2 y0 plus yn plus 2 lots of all the y's in between the given 2 values that appear only once. So all the others will appear twice. So this is going to be a y0, and this is going to be yn. This is the last value, and these 3 in there are the ones you're going to put in the brackets. What is the value of h? The value of h is the gap here between these 2 values. It's pi over 12 minus 0, so it's pi over 12. Double check, do 1 6 minus 1 12 is pi over 12 as well. So this is correct. So h is equal to pi over 12. So all you need to do is put this into the formula and then use the calculator to evaluate it. y0 is 1. The last value is 2. 2 lots of 1.035 plus 1.155 plus 1.414. And pop it into the calculator, and so we've got pi over 12 in the numerator, over 2 in the denominator, open brackets, you've got 1 plus 2 plus 2 lots of open bracket 1.035, add 1.155, add 1.414, close brackets, the first bracket and the second bracket. It's 1.336. This is 1.34 to 2 decimal places. There you go. If the question asks us to find more accurate answer, what you could do is split the interval between 0 and pi over 3 into more strips. So you could go every pi over 24, for example. Make sure that you are, if you're putting those into the calculator, whenever you open the big bracket, you've got to close it there. Mistake is to not to close it, the brackets, so not to put the brackets in very often, because the formula is quoted in the formula booklet. It's got those two set of brackets surrounding y0, yn, which I think they are unnecessary, and students open that bracket and forget to close it, and then what happens is just they were on the first value will be multiplied by the half of h, which give totally wrong answer. The best thing to do is always check, go to your integral evaluator and put the function, so the integral of sec x between 0 and pi over 3, and see how close you are to the real answer. If you are far off, or then you know you've possibly put something incorrectly into the calculator. Right, so I hope that will be enough for you to have a go at exercise 11i.